Welcome to this explainer. Today we're diving into a really fascinating, fundamentally deep question. Where does intelligence actually come from? We're going to take a calm, academically grounded look at the interplay between data, structure, and something called the energetic paradigm. Finding the right balance between these forces is becoming absolutely critical, whether you're a researcher, a technically informed investor, or an enterprise leader trying to map out the future.
Here's our roadmap for today. We're going to start with the dominant scaling narrative, then move on to the deeper theoretical question underlying it all. From there, we'll spend some time exploring the energetic paradigm, take a hard look at scaling costs and limits, and finally wrap up with a synthesis for intelligence.
So let's jump right into Section 1, the dominant scaling narrative.
Look, when we talk about AI today, the standard playbook is pretty much universally understood. You gather larger data sets, you build increasingly larger models, you extend the training duration, and you throw a truly massive amount of computational power at the whole thing. The end result? Drastically improved capability. Over the past decade, this brute force approach has undeniably driven the entire industry forward. We absolutely have to acknowledge that it works, and honestly, it works brilliantly.
But that leads us directly into Section 2, the deeper theoretical question.
Because this brute force scaling has been so wildly successful, we really need to pause for a second and ask a fundamental question. Does capability arise only from scale, or does it also come from the structural conditions within the system itself? We all know the old saying, correlation doesn't automatically prove causation. So we have to ask ourselves, is intelligence strictly the result of accumulated experience, or do a system's internal constraints actually play a foundational role?
Well, data and structure actually play two completely different complementary roles. The standard learning process relies heavily on data for exposure, for extracting patterns, and for optimization. Basically, data expands the variation of what a system knows. Structure, on the other hand, determines evolution. Instead of just relying on soaking up massive amounts of experience, structure actively compresses the space of possibilities. It stabilizes the system's behavior over time.
To really grasp this, we kind of need to reframe how we think about capability. Abstract concepts like reasoning or planning aren't just magic. They are stable behavioral patterns. In any dynamic system, unstable or contradictory behaviors naturally collapse on themselves. Coherent patterns, however, persist. They show up repeatedly, specifically because the system's underlying structure allows them to remain coherent.
What this means is that a system doesn't necessarily need to blindly wander through a vast landscape of possible behaviors if its internal constraints already naturally favor coordinated, stable states. Ultimately, intelligence is not only what is learned, but what structure allows to persist. Which naturally brings us to Section 3, exploring the energetic paradigm.
Rather than just asking, hey, how much data has this model absorbed, the energetic paradigm shifts the focus entirely. It looks at energy configuration, state constraints, path stability, and information flow. Think of it like water carving a canyon. The water is the data, sure, but the energetic constraints of the rock actually dictate the most stable path for that water to flow. This framework asks how a system's internal organization organically shapes viable behavior.
So how does this actually work in practice? It comes down to three specific structural mechanisms. First, you have feasible state compression. This simply means there are fewer viable states that can persist, so contradictions collapse very quickly. Second, pathway stabilization creates a coherent flow of information, which makes reasoning much more reliable. And third, early filtering ensures that those unstable patterns disappear early in the process. Now, it's crucial to note, these constraints don't replace statistical learning. Rather, they reshape the very environment where that learning happens.
By cutting down on all those dead-end, ineffective behaviors a system usually has to experience, we're hypothesizing some pretty significant payoffs. We might see much more stable reasoning, improved coherence in planning, drastically reduced inefficiency, and just greater overall reliability. Keep in mind, these are currently hypotheses, but they represent the incredible potential of guiding a system toward coordinated states rather than just forcing it.
Now, let's ground this in reality with Section 4, scaling costs and limits.
All these theoretical benefits we just talked about, they hit right at the heart of the practical realities and headaches the industry is facing today. Brute force scaling requires enormous data accumulation, vast financial costs, and absolutely massive energy expenses. While it remains highly effective, these relentlessly rising costs are exactly what's motivating researchers and investors to explore structural design. It's becoming a highly necessary alternative, or at least a necessary companion to scale.
Which brings us to our final point in Section 5, a synthesis for intelligence. If we look ahead, future progress is almost certainly going to depend on a second axis of development. On one axis, we have our traditional data scaling, taking massive inputs to expand experiential coverage. But on this new axis, we integrate structural design. We utilize state-space constraints, pathway stability, and behavioral control to filter those trajectories and stabilize behavior. Moving forward, mature intelligence will absolutely require the thoughtful integration of both.
It really boils down to this elegantly simple idea. Structure provides order. Data provides variation. Think about it. Data without structure leads to massive but wildly unstable capability. Conversely, structure without data yields a system that is incredibly stable but severely limited in what it can do. Both are fundamentally necessary if you want to integrate experience into genuinely coherent behavior.
By adopting the energetic paradigm, researchers can start moving beyond standard data metrics to ask some truly novel questions. Which internal states are actually viable? Which behavioral paths naturally persist? How is instability filtered out early on? And how does coherence naturally emerge from the architecture? Experimenting with these specific questions is going to help us figure out if structure can actively reduce our massive training needs, or perhaps enable earlier, more robust capability.
For the enterprise leaders and technical investors tuning in, the practical relevance of this is huge. Now, we need to be measured here and acknowledge that these outcomes aren't universally achieved just yet, but a structural approach represents an incredibly compelling goal: developing systems that are far more mathematically efficient to train, inherently more stable, and fundamentally easier to manage at scale.
As we wrap up this explainer, consider this. The future of artificial intelligence isn't just going to be a simple race for who has the biggest datasets or the largest computing clusters. True maturity in this space is going to belong to those who understand how to carefully shape the structural conditions of intelligence itself. As the physical and financial limits of brute force scaling start to close in, the most critical question for the industry becomes, are we just building systems that memorize the world, or are we building structures that are designed to actually understand it?